Hey everyone, this is our final video for the ellipse. In this video, we're going to be look at shifting the center of our ellipse from the origin to a random point of HK. And then we're also going to look at a few applications for the ellipse, okay? So on your screen here, you can see you have two of these graphs for the ellipse where the center has been shifted to the point of HK. And notice how that affects our equations for the ellipse. You simply just have to subtract the values of h and k from x and y before you square them in your equation, all right? Also, one really important thing to notice is that when you move your center away from the origin, you are moving your major and your minor axes, okay? So notice the ellipse that's on the left here, your major axis, it's still horizontal, and we want to think of it as being parallel to the x-axis. And I can reason that out from the equation just in the fact that that first fraction that involves the variable of x, it has the larger denominator of a squared. The graph that's over on the right-hand side, you can see the major axis is a vertical line parallel to the y-axis, which we can identify from our equation by simply looking at the fact that the larger denominator is underneath the variable of y. All right, so get right into an example. Find an equation of an ellipse whose center is at -3, -1, whose vertex is at -3, 3, and whose focus is at -3, 0. So plot what we're given here. Right, there's your center. Here's one vertex. And here's a second, here's another point, which is the focus. Okay. Notice all three of those are lining up on this vertical line. So that's my major axis right there. I'm going to give an equation for that of x equals -3, and more importantly, I'm noticing that this is a vertical line, which means it's parallel to the y-axis. So that tells me when I go to write my equation for this ellipse, I'm going to have the larger denominator of a squared underneath my variable of y. All right. I can also tell that my a value is 4. That's the distance from the center to the vertex that was given. And I can use it to plot my other vertex, which is down here at -3, -5. My c value is 1, distance from center to the focus that was given. And I can plot my second focus at -3, -2. The only thing that's stopping me from completing the graph as well as the equation is my b value. So I'll find that with b squared equals a squared minus c squared. So a squared 16, c squared's 1. That's going to make b squared 15, and b the square root of 15. So from the center, I'm going to move radical 15 units to the right and to the left of it to get to my co-vertices, okay? So radical 15 is just under 4 units. So if I move right from the center, radical 15 units places me right around there, and left places me right around there. So right here is the ellipse, okay? And I want you to be able to give me the exact coordinates of those co-vertices. All right, now here's how we would reason those out. If you moved from the center left and right radical 15 units, that essentially means you are subtracting or adding radical 15 from the x coordinate of the center. Now the x coordinate of the center is -3, right? So co-vertices can be described as -3 plus or minus radical 15, comma, -1. Okay. All right, now I can write my equation here. take the center into account. So if the center is got an x coordinate of -3, then I have to add 3 to x before I square it. And if the y coordinate from the center is -1, I need to add 1 to y before I square it. And of course, this should be equal to 1. And then I need to put my a squared and b squared values in my denominators. A squared is 16. It needs to go underneath y since my major axis was parallel to the y-axis. That makes 15 underneath x. And there we have it. All right, some applications of the ellipse. So our solar system is made up of several planets that all orbit around the sun, right? And the path of each of those planets in orbit is an elliptical path. Many people think it's circular, but actually it is elliptical, okay? A second application where an ellipse shows up is in what's known as a prolate spheroid. And a prolate spheroid is essentially taking an ellipse and rotating it around the either x or y axis, around its major axis, in order to create a three-dimensional shape, okay? So let me load this here. All right, so notice I have half of an ellipse here, and the major axis of that ellipse would be this red axis, all right? And if I start to rotate that around that major axis, I'm going to get this three-dimensional figure formed. So you can see the rotation happening. I'll speed this up a little bit. Okay, so in the end, this is what we're getting. That's known as a prolate spheroid. Some of you might be thinking that looks like a blimp, which I would not disagree with you. But it is also a football, all right? So that's interesting that you can create a football by using an ellipse, all right? So if we go back here, a prolate spheroid is also known as a football. Pretty cool.